Okay, good morning. So let us start today's lesson. So if you remember last time we talked about Hamiltonian graphs, and then Hamiltonian graph is a Hamiltonian that contains at least one Hamiltonian cycle. And Hamiltonian cycle is just a cycle. Cycle means that you will start from a point on the graph, go around the graph on the edges and vertices. You are not allowed to repeat any vertices at all, but you have to come back to the same starting point. If you can find a cycle like that, which covers all the vertices of the graph exactly once, and return to the same point that you started with, that cycle is called the Hamiltonian cycle. And if we have a graph containing one of those cycles, that the corresponding graph is called a Hamiltonian graph. Yes? And we talked about this, that a little bit, that of course there are no algorithms there are no theorems, if and only if theorems, that by just looking at the graph of the function, the graph of the diagram of the graph, I can immediately realize that the corresponding graph is Hamiltonian or not. And if you want to do it using a computer, that's also a famous problem. That is, the algorithm that you use for this is exponential. It's exponential time. Yeah, it takes exponentially. So if you increase the number of vertices bigger and bigger, the time that you have to, the number of steps in the algorithm that you want to execute to see that if this graph is Hamiltonian or not, grows exponentially by the number of vertices. So if the number of vertices become large, even for computers, it is very hard. So that's an exponentially hard problem in computer science. Okay, and this graph is related to a solid object called dodecahedron. And then we will talk about these things a little bit, not too much. But this is a famous graph. I couldn't draw it very carefully. It's completely symmetric. I just want to wait a little bit for you to see if this is Hamiltonian or not. You see, if you want to say it's not Hamiltonian, at this point you need to know a little bit of more advanced theorems, including necessary conditions for a graph to be Hamiltonian. And if those necessary conditions are not met, you can just conclude that, okay, this graph is not Hamiltonian. But if you want to show that this is Hamiltonian, there is only one way for you: to sit down, do some trial and error to determine a Hamiltonian cycle in this graph. So I didn't remember if I exposed that. Yes, this graph is Hamiltonian. I want to give you a little bit of time, 5 minutes. If you have already done that, let others think about this. Find a Hamiltonian cycle, and then I will ask to read it for me. If it was correct, we accept it. Otherwise, I tried my own way. I will write it down here for you. Okay, so I will pause this recording for 5 minutes, and I want you to find a Hamiltonian cycle in this graph. Okay, anyone could come up with the answer? Yeah, can you just read it for me, if that's okay? We just write yours. So let me bring that myself. Okay, Sanders, can you just tell me what is that? A, let me just write A, B, then
to C,
C, D, E, F, T, S, what, N? M, okay? L, K, J, I, P.
What's that below P?
Ah, okay, so that's my mistake. So let me, this is, my naming is wrong. So let me change it to, I don't know, U, for example. Okay. U, N, R, Q, G, H, then A. Okay, let us check. So yeah, we can because if that's okay, let us. If it's not okay, I will come back to you. So if you see, first of all, the first one is A, the last one is A. That's okay. That's a cycle. And when I see nothing is repeated, so none of these letters is repeated, so it means that I am repeating. I'm not repeating any vertices, so that's okay. So the only thing that I need to check is that if it covers everything. Yes. So also A, and then B, and then C, and then D, yes, and then E, and then F, T, S, M, L, K, J, I, P, U, N, R, Q, and then G, H, A. And I think it covers everything. Yeah, that's completely correct. So this is a reason that why this graph is indeed Hamiltonian, because we were able to find a Hamiltonian cycle in our graph. And of course, again, let me repeat that there are many edges that we haven't used, or have we used all the edges? You can check. So from A to B, we have used this. Many of them are not being used. For example, B to C has been used. C to D has been used. D to E, and E to F, F to T, and T to S, S to M, M to L, L to K, K to J, J to I to P, and then P to U, and N to U to N, and N to R, and R to Q, and then Q to G. So you see, so this one, for example, was not used. Q to G, and G to H, and then H. So probably you can see there are some edges without any red markers on them, yes?
Mr. Balak,
Yes?
is it possible that there is some kind of theorem that predicts how many edges will be unused if it's solvable?
Yeah, and answering these questions, if you don't have exact knowledge about that, it would be extremely hard. I cannot immediately answer that. Yeah. But you see that there are there are many edges that you are not using in this cycle, and that's completely okay. We were supposed to cover all vertices, but we don't have the obligation to cover all edges. And we did that. So this is a reason why this graph is Hamiltonian. Okay, now let us start a little bit of new stuff here, today. So, definition of a planar graph. Okay, so what I want to define for you here is the notion of a planar graph. It means that a graph that you can embed it on a plane. What do we mean by that? So, a graph G is said to be planar if it can be drawn in the plane in such a way that intersecting edges in a diagram of the graph intersect only at vertices. If G has no such representation or diagram, then G is called non-planar. Okay. So what does it mean? For example, this graph G1 that you see on the board is actually a planar graph. Because whenever you see intersecting edges, that is a vertex. Okay, for example, this edge and that edge are intersecting at this point, and this point is actually a vertex. So that's no problem. Yes. For example, I don't know, this one and that one are intersecting, but this is a vertex. But for example, here, this is what I mean. This is not a planar, at least, representation. For example, you see that this edge and that edge are intersecting, but this is not included. So you see, I told you that by convention, if I want to show a vertex in a diagram of a graph, you really need to make it clear that these are actually vertices. When I do not do that, it means that this is not a vertex. But now look at it. This edge and this edge are intersecting at a point, but that point is not a vertex. So either, there are two possibilities here. Either this graph is not planar at all, which we call it non-planar, or you can draw it in a different way, which is isomorph to this. Do you remember the two isomorphic graphs? It's isomorph to this. It means that the relation between different vertices are held intact, but it doesn't include this intersecting point. If that is the case, if it is possible, it's not guaranteed that it's always possible. But for example, can you see this graph is planar? This representation is not the planar form of that, but can I change it to an equivalent, which is called isomorphic graph? Can I draw a graph which is isomorphic to G2, but we do not see this intersecting point between these two edges, which is not actually a vertex? And I think it's very easy for you to do it for me here. Yes, I can just draw this graph. So everything I am keeping, I draw this one. I am supposed to connect this vertex to that vertex. If I draw it in that way, I will have an intersection which is not a vertex. But is there any way that I can go around it? The answer is yes. I can just do it like this. Yes? I hope that you agree with me if you remember what we talked about isomorphic graphs. This graph is actually the same graph. Yes? This represents the same graph with a different diagram. So, but the point is that now nothing is like this. Every two edges that are intersecting, they intersect at vertices. So this is not this is a planar graph, because at least I was able to draw it in a way that the edges intersect exactly at vertices. If it is possible, the graph is called planar. If it is not possible, then the graph is non-planar. And I think that you immediately understand that this is not an easy subject at all. How can I understand that the graph is planar or not? But fortunately, this has been proven by mathematicians, but of course we will not be able to go delve into this that much. But there is a theorem that you can somehow understand if the graph is planar or not. For example, here, is this graph planar? If you trust me on writing it, it should be a planar, but at least you realize that this is not a good representation if this is going to be a planar graph. So then I ask myself, is it possible to draw it in a planar form? Can I represent it in the planar form? Yes? So how should I do that? For example, let me put these two dots here. So let us see what's happening. 3 dots here. So nothing is between these two. No edges are between these pairs. But every one of these vertices is connected to all the vertices here. Okay, so let us, for example, do the first one. Nothing that I can avoid. So let me just draw this one. But look, here I want to avoid intersections, because intersections should only happen at vertices. So for example, I don't have any problem here, so I just connect them. But what I need to do, I connect this one from this side. No intersection happens here. And then I can connect this to this one. Yes? So hopefully you agree with me, even though the diagram is totally different from this diagram, from geometrical point of view, they are totally different shapes, diagrams, but you realize that whatever this diagram represents as a graph, this diagram also represents the same graph. Okay? So from this graph is isomorphic to that graph, but you see that here, if an intersection happens, that intersection point is a vertex, nothing more. So this is also a planar. Okay? So this is a planar representation of this graph. So we had a planar representation. But if, for example, if I ask you the same, so this was a very famous question. I think it also starts from solving a riddle or a conundrum, so I don't remember exactly. But so this is a famous graph. So I want to do the same thing with 3 dots here and 3 dots below, yes? So I have 3 dots here, so let me draw it black. So this graph is also famous in graph theory, and they have given it a name. So it's called bipartite graph. Let me check the name. I want to check the name if that's spelling and everything is correct. And there is a name for that. They denote it by K3, 3. Okay, so it means that a bipartite graph is a graph that you have 2 distinct vertices, 2 distinct set of vertices. These are not connected to each other at all. These are not connected to each other at all, but every vertex here is connected to all the vertices from the other collection. Okay, so that is, if I want to give the same name here, I would call it K, 2 points, 3 points. So that's also a bipartite graph, yes? I will check this spelling and the pronunciation here now. Okay, but now, can I do the same thing here? Can I connect every one of these vertices to all of them, avoid unnecessary intersection points, avoiding unnecessary intersection points? Okay, you can check this a little bit so that I can find this, the correct name if I have spelled it correctly. Yeah, please try to do that, yes? To see if it is possible. If it is possible, this means that K3, 3 is planar. If this is not possible, you understand that's the hard situation, because you might say that I couldn't find it. It doesn't necessarily mean that no one can do it. So you see, you are in a very hard position. If you can find it, it's finished. If you cannot find it, it's not clear that if you couldn't find it or no one can find it. So I just want you to understand this distinction.
Bipartite.
Bipartite. Yes, so the spelling and everything is correct. Okay. I don't know, because this is one. I just want to give you the information. This is one of the most famous non-planar graphs. So this is one of the building blocks of, if you understand, if you can detect this type of graph even inside another graph, then immediately you realize that this graph is not planar. So this is one of the most famous non-planar graphs. Okay, hopefully. I don't know, you can try to convince yourself that at least it is not possible immediately. So for example, if I want to connect this to this, let us just connect them. I don't need to be careful at all. But for this one, I have to be careful. So for this one, I don't need to be careful. For this one, I don't know, I can go from here and connect it to here, and for this one I can do the same thing here. But for example, you see for this one, I can still do it. Okay, let me just do it directly. I think you can still do it a little bit better than I did, yes? So how many edges are left now? I need to draw 2 more edges from here, but this is a dead end. The way that I did it, I need 2 more edges. I don't know, could you come up with an answer that you need only 1 edges to be drawn and you cannot do it?
Yes.
Yes? Okay, can you tell me what to do with? You see, at least, so you see, if I want to be convinced that this is not planar, it means that I am not careful, because now Alex is saying that he was able to find a different drawing. Here, how many edges I need to draw? I need to, okay, I can do it here, by the way. I was a little bit careless myself. Yes, thank you. We can do it here. So that's also possible. Now there is only 1 edge left. So I need to connect this to that. And hopefully you see that, at least in the way that I drew it, it's not possible if I want to, if I do not want to intersect any one of these edges. It's not possible. Yes? Okay, so people probably were a little bit busy with this doing and then realized probably it's not possible, and then try to show that this is not possible as a mathematical theorem. Okay, so remember, another famous non-planar graph is called K5. K5 is just, it means that you have 5 vertices. These are called complete graphs. So let me just talk a little bit. So if I say K1, it means just 1 dot. If I say the complete graph, I don't know, for some reason it is denoted by K, not C. But it is called a complete graph on 2 vertices. So it means that you have 2 vertices, you connect them. And K3 is just your famous triangle, yes? All of them are planar, if you see. And this is K3. Okay, so what is K4? Complete graph of order 4 is just a square. And no, sorry, it's not a square, because you are supposed to connect all the vertices together. So it means that this vertex should also be connected to that vertex. This vertex should also be connected to this vertex. But you realize this is it's a planar graph, yes? That's exactly G2 in this picture, and we were able to show that this is planar, yes? But here, so up to here, K1, K2, K3, K4 are all planar graphs. For this one, look at that diagram. But if you go to K5, this is also another famous graph, which is not planar. It's a non-planar graph. So it means that I have 5 vertices this time, but I have to connect every pair of these vertices together. So it becomes a pentagon. And of course, this should be connected to this. This should also be connected to this. This should be connected to every one of these. So this is already connected, so I have to connect it here. I have to connect it here. And then when it goes here, I should also connect this one. So this is a star. And then you remember that that's also, this star is also isomorphic to this pentagon, okay? So this is K5. This is also non-planar. So it is not possible to draw this in a way that you can avoid these unnecessary intersections. So let me write this as a remark, yes? K33, what I told you here. So, and K5 are famous non-planar graphs. Okay, any questions? Yes, please.
I think these theorems are very useful in electronics.
Exactly. I didn't remember to talk about that. Can you elaborate more?
Well, if you're trying to phase out components and you have a PCB, a card which has the connections on it.
Exactly.
And if you want to be very cheap and
Yeah, exactly. Because, for example, they need to understand that because if these are, for example, if you're designing a motherboard or something, probably these are unnecessary connections. This would give you shortcuts, yes. So it will destroy the whole circuit. So it means that you should be able to see that if it is possible to avoid these kinds of things, these kinds of shortcuts. Short connections, not shortcuts, sorry. So these are short circuits. Short circuits is the probably physical terminology for that. So if if these are just wires and I am just drawing it like that, then automatically I will have a short circuit here. If this is not supposed to be there, then this will destroy the whole motherboard or something. So these kinds of things are very important even if you want to do it in industry. So yeah, there are many very applications for graph theory, even outside the world of mathematics. Mainly is computer science, but as Alex actually pointed out, yes, that's also very nice. That there should be a nice. I haven't Googled it around, but I think it's completely relevant to designing motherboards, circuits and motherboards and something like that. Yeah, we can check it together, and if you have come up with a good and nice applications, let me know about that. We can talk about this. Thank you anyway. Okay, so now let us define another idea, and that is the notion of a region in a planar graph. When I write the definition, it becomes a little bit lengthy, but I would try to write it down because if you want to read it in the future, you have something to refer to. Okay, so yeah, the idea is so simple, but let me just write it down formally for you. So definition let G be a planar graph. By the way, I don't know, accidentally I drew all the graphs, simple graphs, but that's also a planar graph, for example. It's a multi-graph containing a multi-edge and a loop. That's also planar. So this notion of planar is completely okay if you have a multi-graph. Okay, so let G be a planar graph. It's important. So let me emphasize here. So this definition is only for planar graphs. Consider any planar. Usually they don't call it representation, they call it embedding. This is the usual word we use, but that's the meaning. This is the same. It means planar representation. Consider any planar embedding of G in the plane. So it means that consider any planar representation of G. A region, this is the thing that I want to define for you. A region in this planar embedding is a maximal section of the plane in which any 2 points in that section can be joined by a curve that does not intersect any part of G. The number of regions is usually denoted by R. The small letter R. Yeah, that's a very simple idea. Everyone knows this intuitively, what's the meaning of a region in a planar graph. So let me consider the previous example. So example, consider the same graphs. Consider the following graphs. The following graphs of the previous example. So do you remember G1 was such a graph, so it was like this. So what do I mean by a region? And I want to see how many regions are there. So let me write here. In each case, determine R. Okay? So I want to see how many regions are there. So a region, first of all, if you are sure about that your graph is planar, then only in that case the notion of region makes sense, because the notion of region is only defined for planar graphs. And for planar graphs, if you want to know the region, first of all, you need to have a planar representation embedding of your graph. Okay? If, for example, this is already a good in a good shape for me, yes, because this is a planar and it is a planar representation of my graph. So I can start my job. So how many regions you see here? A region is a maximal section of the plane that if you consider any 2 points in that section, you can connect that 2 points with a curve or a straight line. It depends which one is more suitable, so that that curve will not intersect any part of the graph at all. So for example, it's clear, this part, this triangle you see, this interior point of this triangle is one region for this graph, yes? So because, for example, if I consider any 2 points in that particular part, then I can connect them with this curve, for example, or a straight line, without intersecting the graph itself at all. Yes? So this is one region. Can I, if I go here, can I, for example, is this one and this one, should I consider them 2 regions? Let me consider this. This one and that one. This is one region, this is the second region. I cannot consider this as one region, because if I choose point here and a point here, it is not possible to connect these 2 points without intersecting the graph itself. So if you consider this part one region, this should be considered another region. So let me just call it 1. If you have problems, I think these ideas are so intuitively clear. When I explain them, I'm making them harder. So here, this is one region, this is the second region, this is the third region. Do you think this is all or no? Are these the only regions, or we have more?
Is it the whole thing one giant big region?
Yes, outside. Thank you. So everything outside, so we have 4 regions. If I ask you what is R in this problem, it's just 4, not 3. One big, the whole outside this. So 1, 2, 3, 4. This is the whole scenario. Yeah, let us just go quickly to the G2. But you see, G2, this is a very deep question, by the way. Before doing that, before let me just consider G2. So do you remember another name for G2 was K4, complete graph of order 4. So here, if I ask you, determine the number of regions in this graph, immediately you realize something is wrong, because either this is not planar at all, or at least this is not a planar representation of my graph. So if this is going to make sense, you need to understand if this graph is planar or not. If this is yes, you need to draw a planar embedding of that graph. So we did it before, so I draw it in that way. So the first step that you have to do, you need to represent it as a planar graph. Okay, so it was possible, it was a planar graph, so the notion of region makes sense. And then you start counting them. So for example, this is number 1, number 2, and then probably you agree with me, this whole part now is number 3, and as before we have something outside. Oops. And that is number 4. I hope that I didn't destroy. No. Okay, is that understandable? Do you still understand that there is a deep question going on here? Because you see here, I am using the article the. The number of regions is usually denoted by R. So do you think that this makes sense? It's not trivial. Do you agree with me? Because if the graph is complicated, how do you know that? Because for example, even in this simple case, I can draw it in a different way. So for example, let us consider this one. Of course, this is so simple that you might think it's trivial, okay? But at least from this picture is not identical to that picture, even though all of them are representing the same graph. But if I ask you count the number of regions here based on this drawing, you will get the same number. You see 1, 2, 3, and then 4. So it is extremely important to understand. Pardon?
What about the one where you first draw a triangle and then put a dot in the middle?
Okay, just if you are finding this, it means that this, because as far as I know, this is a theorem. This is a theorem that this is important. When you talk about the number of regions, you need to be able to show that this number is independent of how you draw the planar representation of your planar graph. If it depends to the way that you draw, in this graph it was so simple, the idea was more or less clear, but assume that you have a complicated graph and you know for some reason that this graph is planar, but there is not a unique way of drawing the graph. And by the way, this is very sensitive. It seems to be very sensitive about the way that I'm drawing these edges, because I'm counting the number of regions. Yes, it seems extremely sensitive, but apparently it is not. So it doesn't matter if you come up with just one representation of your planar graph. No matter how you drew it, the number of regions remain the same. And that is the good point. So it's already a highly non-trivial theorem behind this that you can call the number of regions. Okay, but at least if you agree this theorem, then you can immediately, not immediately, it might be hard to redraw it in a way that it is a planar one, but counting the number of regions, yeah, I don't think that's a hard problem. At least for understanding it, yes? Okay, so for example, let me do the other one as well. So here, if someone asks you what is R, again, you will give the same answer for this graph. R is 4. But now let me do G3 here without cleaning that part. So do you remember what was G3? G3 in our picture was K2 and 3, the bipartite graph with 2 vertices and 3 vertices. So it was like that, if you remember. So in this way, don't get confused. You are not allowed to start counting the regions in this form, because this is not a planar drawing of this graph. So first of all, you need to redraw it in a planar form and then start counting the number of regions. So do you remember what we did? We actually, I think we did like this. So we connected these three as before, and then that was simple. And now I need to connect this one with that one. So I don't know if I did it like this, and then I did this one like that. Okay, now let us count the number of regions. So I was not able to, so don't think that this is one region, 2, 3, 4, I don't know, 5, and then 6. It might, I don't know, it might be coincidentally the same number, but don't do it in this form. Immediately you can convince yourself by different graphs that the number of regions will change if you just go from here to here. Okay, but this is the way. So hopefully you agree with me that the whole part here is just one big region. And the same scenario here, yes? So here I have the second one. Yeah, this is exactly a good example. Is there any other one?
Yes, the outside.
The outside, so it is 3, not more. So the number of regions is equal to 3 in this case. Okay, so you see, if you wanted to count the number of regions here, it was totally wrong. You might say that this is one region, this is the second region, third region, 4, 5. So this is not the same. So the number of regions is 3. Okay, hopefully that's understandable. Okay, let us discover a little bit more here. I want to give you a task, because you know that in graph theory it is fun to discover at least the relations. Proving the relations might be quite hard, but exploring them, at least for simple cases, shouldn't be that hard. Okay, so let me just give you an exercise. I want to draw some pictures here for you. So this is example, another example. In each of the following planar graphs, okay, so this is a good exercise. In each of the following planar graphs, specify explicitly P, Q, and R. Do you see a pattern between these numbers? Okay, so do you remember, P is the order, the number of vertices, Q is the size, the number of edges, and R is what we learned today, is the number of regions in planar graphs. Okay, I want you to do this as an exercise. Try to see if you can tell me the pattern. Okay, so just after finishing this, I will give you some time to explore it yourself. So this is G1. G2, let me give you a multi-graph. A triangle here, one loop here, another big loop here. Okay, and then a multi-edge here, and another loop here. So this is G2. So yeah, it's not very good picture, but you understand. There are 2 loops on this vertex. Okay, and then G3, I have a bigger triangle here. Find the center somehow, connect it here, and then some leaves. Do you remember? Vertices with degree 1 are called leaves. So this is your G3. Let me draw G4 as well. So I am emphasizing on the dots here. I have to emphasize. So hopefully it is clear. So 1, 2, 3, 4, yes. This is G4, and the last example might be also good to know for the future at least. G5, something like this. There is, of course, there is a particular name for this graph, and I saw that in the exercises of the book they are explaining. So if you have a graph which is connected, one piece, and it doesn't contain any cycles, it's connected but without any cycles, that graph is called a tree. Tree, yes? Just the name, I want you to know the name. And if you have more trees, disconnected trees, that's called the forest. Yes? Okay, so I paused the video from being recorded. I want you to find P, Q, and R in each one of these, and then try to see if you can discover a pattern among these three numbers. Okay? Okay, could any one of you come up with a pattern? Yes, may you please tell me what the pattern is?
If the order of the graph is greater than the size, then the number of regions is equal to 1. If the order is equal to the size of the graph, then the number of regions is 2.
Yes.
And if the size is greater than the order of the graph, then the number of regions is 2 plus the difference between the size and the order.
Okay, but what you said, very nice. So I think your pattern is correct, but all of them can be combined into one single formula then. Yes, what you discovered I think is correct except for the first one. The second one and the third one, what you mentioned was correct. For the first one, I think it was also correct, but you are distinguishing three cases, which if you think a little bit deeper, you realize that all of them can be put into one single formula, which is called Euler's formula. Okay.
Is that formula
Q minus P plus 2 is equal to what?
R.
Yes, yes, that's correct. So if you Sanders, if you check back, what you discovered is exactly what Alex mentioned in this simple formula, and that is called the Euler's formula. Let us try to discover that, write this, and then end the lesson today. So here, for G1, what is P? It's clear. P is the number of vertices, Q is the number of edges. You immediately count them, it is 4. And if I ask you what is the number of regions, it is 2. Because I have one region here and the second region outside. Okay? And now let us go to G2. So for G2, how many edges do I have? I have 3 loops, so 3 edges, a triangle, so it is 6, and one multi-edge here, so 7. Yes? If I make a mistake, please let me know immediately. So, the number of edges is 7. What is the number of vertices? So I have just a triangle, yes? So the number of vertices is 3. And if I ask you what is the number of regions, how many regions could you realize here? So one region is this one, the other region is here, 3, 4, and 5, 1 outside, 6. So I have 6 regions. And then let us go to G3. So G3, how many vertices do I have? So here I have a 1, 2, 3, my triangle, 4, and 3 more, 7. Yeah, please, if you see that I'm making mistakes, let me know. So Q. I have 3 edges for my triangle, 3 edges inside, 6 and 3 edges here, so 9. And then how many regions do you see? Yeah, I have 1 region here, 2, 3, and 1 totally outside, yes? So 4. And then G4. G4 is this one. So how many vertices? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 vertices here. And how many edges I have? I have 1 big triangle, 1 small triangle, 6, 7, 8, 9. So Q is 9. So Q is 9. And what is R? R is 1 inside this small triangle, 1 region, and then everything here is the second region, and everything outside is the third region. Yes? And then G5. G5, if I ask you what is P, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then what is Q? Q is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what is the number of regions, by the way, in this problem? What is R?
1.
It's just 1. Yes, if you don't understand something about R, please let me know. So R is actually 1 big region. And by the way, you need to check if all of them are planar. All of them are planar. Okay, so the discovery is this. So this is the nice formula discovered by Euler, actually. So the formula is P minus Q plus R is always equal to 2. So P minus Q plus R is 2, so that's correct. P minus Q is how much? Is it wrong here? Yes, now I realize why Sanders makes this. So this pattern is not correct here because this graph is a multi-graph. So probably this is always for simple graphs. Let me check. I don't exactly remember. So here P, so let me see. P minus, so all of them are simple graphs except G2, yes? So let me check for this one. 7 minus 9 is minus 2 plus 4 is positive 2. So that's also okay. And 8 minus 9 is minus 1 plus 3 is 2. That's also okay. And 10 minus 9 is 1 plus 1. That's also okay. So might be, you are right, I think might be forgotten something. And then you see that here it is not correct. Yes, 3 minus 7. Am I right in counting them? Yes. In G2, yes, yes. So in G2, 3 vertices. Do I have more vertices? No. I have only 3 vertices, so I haven't done something wrong. 1, 2, 3 loops, and then 6 and 7. Yes, everything is right. But you see that this violates this rule. So probably, so you were correct completely, Sander. So that is not related probably. This is related that this formula is only valid in simple graphs. I need to recheck. I don't remember exactly. Might be this formula only because you see that in all these graphs that the graph is a simple graph. This pattern emerges, but exactly for this case where G2 is not a simple graph. Is it true?
3 minus 7 is...
Yes, it is correct, yes. Yeah, thank you very much. So I need to review my elementary school problem, yes. So 3 minus 7 is how much? Is minus 4, yes. I don't know why I was confused. Plus 6 is 2. So that is a very elegant and simple formula discovered by Euler, and he was able to mathematically prove that. Okay, so the reason that I am confused here, I don't know, when I was writing some notes, I saw that I have written if G is a connected planar simple graph, I don't know why I emphasize on the simple one. Okay, I will check it again to make sure that I am not doing something wrong. But for the time being, this is the formula. It's a very simple and nice formula that if you have a graph which is planar, and if you draw a planar way of doing it, and then you start counting the vertices, the number of vertices, edges, and the number of regions, this simple, very nice formula is holding among those three numbers. Okay, so the only thing that I am a little bit doubtful, I need to recheck everything. So that if this is also valid for multigraphs, at least for this example, it was also valid. And I think it should be valid. Yes. Yeah. Okay, so I will not write down the Euler's theorem right now. I will check everything to be 100% sure about that, if it is only in simple graphs or it's in all possible graphs if they are planar. I think planar is probably the only constraint there. Or I don't know, could you come up with a counterexample that you can draw a multigraph which does not follow this rule? Yes, if you can come up with that idea, with that example, it means that of course this is not true for multigraphs. But yeah, I will check it, and then later I will formally write the Euler's formula. So I only need one more session to finalize that, and the next week we will continue to the next chapter, which differential equation. Might be because Morten said that he doesn't need his lessons anymore, probably. Yes, I will try to find a way to teach you more on differential equations. And of course, that lessons would be voluntarily. So if you don't, that would be the same time that you were supposed to have physics, but instead of Morten appearing in that class, I will appear. Okay. Okay. Thank you very much. So I will end this recording.